Hello, ninth graders. Today we're going to start our new unit on work and energy. And we actually won't get to energy for a couple weeks. We're going to start out with what we call work. And to you, that might seem like a pretty obvious word. I mean, we use it all the time. I have to go to work. I've got to do my homework. I've been working really hard at coming up with ideas for something. But in science, we have a very narrow definition of doing work. And so, for example, we look at this guy here, famous weightlifter from the 70s and 80s from Russia. And the question is, in this position, is he doing work? And the answer, while he's exerting a lot of effort, the correct answer here is no. He is not doing any work. In the process of lifting that weight, he was doing work, but just holding it there, he is not. So let's take a look and see what work actually is. So work is a force that is applied through a displacement. So you have to push on something and it has to move. And while you're pushing and while it's moving, you're doing work. Now, here's the thing. If you are pushing on something and it's not moving, then you're not doing work. You can sit and you can try to push a wall all day and your muscles can get sore and you can start sweating. But if that wall doesn't move, you did not do any work in the scientific sense. Just trying hard and doing, exerting effort, that is not work. The other thing is when you make something move, only the part of your force that is in the same direction of the motion is doing work. So here's an example of a dad pulling a kid in a wagon, and he's pulling up along the handle of the wagon and exerting a force of 50 newtons. Well, the wagon isn't traveling in that direction. The wagon is traveling forward. Now, some of you might be in a math class where you've talked about how to figure out what the components of a triangle would be. And actually, we've talked about that too when we talked about vector addition and using the Pythagorean theorem. But the point is, and I'm not going to make you do this, but the point is only 43 newtons of that 50 are going toward making the wagon go forward. The other part of his effort is actually trying to make the wagon go upward. So when we figure out work for this situation, only the 43 newtons count, and the distance that he travels, the 30 meters, will count. All right. So here's a question. If I push a chair along the ground, am I doing work? And the answer is yeah. I push it in the same direction as it's going and it's moving. So I've satisfied all the requirements for the scientific definition of work to be fulfilled. Now, if I hold a book up and I walk, am I doing work on the book? And the answer here is no. I'm providing an upward force, but the book is moving forward. So in that case, the force and the motion are not in the same direction, and therefore, again, in the scientific sense, you are not doing work. Right. Now, mathematically, we figure out work using this equation, W, which stands for work, and this is why we didn't use W when we talked about weight, because we just have too many W's. So W stands for work, force stands for, or F stands for force, and D stands for distance. Force times distance is your work. We measure work in a unit called the joule. Remember, force is measured in newtons. Distance is measured in meters. So you get newtons times meters. That's this, newtons times meters. But again, scientists don't want a whole bunch of units. They just want one. So they say, let's call that a joule. All right, I'm going to skip those different, oops, sorry, moving right along. Last thing we're going to talk about here is power. Now, power is the rate at which work is done. If you want to get work done faster, you have to do more, use more power. Here's an example. Let's say that I want to walk up the stairs. It requires a certain amount of force for me to go up the stairs. I have to go a certain distance, so force times distance is my work. Now, if I run up the stairs, I still have to get the same amount of weight up the same distance. The force and the distance are the same. So what's the difference? Why is it harder to run upstairs than it is to walk up the stairs? And the reason is I'm doing the work faster. I have to be more powerful when I do a run up the stairs versus walking up the stairs. And so mathematically, we figured that out by this equation: power equals work divided by time. Another way, since work is force times distance, I can write the equation as force times distance divided by time. And power is measured in a unit called the watt. So why do I have a light bulb here? Because a lot of times when we look at light bulbs, we want to know how many watts that light bulb is. All right, that is it for the notes today.